Hello, I'm Terry Soul, and this is Programming Chaos. For today's project, I wanted to do recursive fractal snowflakes. So there's lots of different ways of generating snowflakes. If you do a search on the web, you'll probably find dozens of different approaches. This one I particularly like because, as you can see, it gives you lots of interesting variety, fairly accurately looking snowflakes. It is not too complicated to program. There's two main concepts that we'll be using to create these fractal snowflakes. The first one is the idea of transforming our coordinate system. So in processing, the base coordinate system starts in the upper left-hand corner and sort of points down and to the right. And it turns out we can move that and we can change the coordinate system. That will be very useful for drawing both the six-fold symmetry of the snowflake and for getting the nice fractal branching patterns. And then the other one is recursion. So a recursive function is simply a function that calls itself, often many times until it reaches some stopping condition. Recursion is a super powerful tool in programming. It's a little complicated to understand at first, but once you get used to it, you'll find that it shows up in all sorts of different applications. So to make these fractal snowflakes, that's the two ideas we're going to be using: transforming our coordinate system and recursion. Okay, so let's get started. Here I have some base code, and this is sort of the boilerplate for processing. So a setup and a draw function that don't really do anything yet other than create a window, and I'm setting the color mode to hue, saturation, brightness, with hue being our 360 color wheel and saturation and brightness just going from 1 to 100, because I think that's a nice convenient range. And then on our second tab, we have the snowflake class. So I'm going to make snowflake objects, but there's nothing in that class yet. And so I'm going to begin with just a simple display function. And all it's going to do is display a single line, sort of the starting branch for our snowflake. Okay, so here's the display function. I'm setting the color, I'm just drawing a line, so I'm setting the color on our color wheel. 180 degrees is sort of a light blue, which I think is a nice sort of snow color. I'm setting the weight of that line that I'm going to draw as being fairly heavy, and so I'm tying it to the width of the screen. So I'm taking 15% of the width of the screen and then 10% of that, and you'll notice the length of the line is also 15% of the screen. So the idea, thinking ahead a little bit, is I'm going to draw a line that's 15% of the screen, and then as we go around to make the snowflake, I'm going to draw a line in the other direction, for example, that's also 15%. So the core of the snowflake will take up about a third of the screen, 30%, which seems about right. So here I'm just displaying, really at this point, just a line, but that's the basis for my snowflake and not a bad place to start. And then if we actually want it to show up, I have to go back to main and create a snowflake object. So snowflake, I'll just call it S1. We then construct it using the new command, and in draw we display it. So there we go. Not much of a snowflake yet, just a fairly thick line in this light blue color up in the corner. So the first thing I want to do to improve this is to shift that to the center of the screen. And I'm going to do it using a coordinate transformation. So let's begin there. I want to take my coordinate system and transform it by translating the origin to the center. And that's the command I'll use, is translate. So this is the translate command, and notice that I'm translating to the middle of the screen, half the width and half the height. So that moves my coordinate system. However, we need a little bit more code in order to get this to work. The extra code we need is this push matrix and pop matrix. And those sound very weird. The transformations that are made to the coordinate system are stored mathematically as a matrix. So we're getting into linear algebra, which we don't have to worry about. But basically, linear algebra allows you to generate a matrix that transforms your coordinate system. And so the push matrix is saying take the old coordinate system and store it. It's actually stored in a data structure called a stack. So we're stacking the old matrix on. We're transforming our coordinate system. So we're creating a new matrix of transformations. And then when we're done using it, we pop that new one we created off the stack, which takes us back to the old one. So you can think of this as store the old transformation, make a new transformation, in this case translate to the middle of the screen, and then go back to the old one. If we didn't push and pop those transformations every time we went through the draw loop, we'd shift our coordinate system further and further down to the lower right, which we certainly don't want to do. So every time we're starting in the upper left and then moving to the center. And so if I run this, we're not going to see much of a difference, except that now our first snowflake branch is drawn in the center where we wanted it. Okay? So now let's take that idea of transformations and use it to turn that single branch into 6 branches. So I'm going to go back to my display and I'm going to use this same notion of changing my coordinate system, but in this case, instead of translating it, I'm going to rotate it. There we go. So I want 6 branches, so I have a for loop that just goes from 0 to 6, or really because it's less than 6, 0 to 5. And I'm doing the same thing. I'm pushing on the old coordinate system so I can remember it, and then I'm rotating by 2 pi times whatever I is, and I see I made a mistake here. This should be 2 pi divided by 6. Right? So I'm taking a full circle, which is 2 pi, dividing it by 6. That's each slice that I need. And then the first rotation is actually 0 degrees. So my first line will be drawn here. And then when we loop through and I becomes 1, now I'm rotating a sixth of 2 pi. And then we loop again, I becomes 2, and I'm rotating 2/6 of 2 pi. So there are different ways of doing this mathematically, but this one I sort of like because it clearly shows 2 pi divided by 6. So I know that each rotation is a sixth of 2 pi, or a sixth of a circle. And then again, I have the push matrix and the pop matrix, so that each rotation, we start again at 0 and then rotate either a sixth of a circle, or 2/6 or 3/6. Notice that I'm indenting the rotate and the line. That's not required, but I find it a little easier to read the code because I can see these 2 operations fall between the push and the pop matrix. Okay, so now let's run this. And there we go. The basis of our snowflake, our 6 lines drawn in a circle. And what's interesting, if you look back at the line, it always starts at 0, 0, and it only moves in the x direction. So really, it's like we're just drawing a horizontal line. But because we've rotated the whole coordinate system, that horizontal line points in different directions. And I understand this feels a little weird. It's maybe a complicated way to think about doing things, but it ends up making the code much easier. Because now what we want to do is add to the end of each of these branches a little recursive branching. And so the idea there is at the end of each of these branches, I want to put in eventually 3 branches. So it's going to be sort of a center branch and then 2 side branches. For now, I'll just put in the center branch so we can see how things are going to work. So here's the code to make that branch. Okay, so here's the code. Now let me explain how it works. So we've drawn our line, And then the next thing we're doing is a translation. So this is, again, taking our coordinate system and translating it. And what you'll notice is the translation here is exactly the same as the end of our line. So I'm drawing a line and then I'm translating to the end of the line. So the new coordinate system, after, for example, I draw this line, the new coordinate system is going to be at the end of that line. So this is where my new 0, 0 is. And then I'm calling the branch function and I'm saying this is the length of the branch I want, which is the length of the old branch times 0.4. So I'm going to make my new branch a 40% as long as my old one. And then the second variable here is a 0, which I'm going to pick up as the depth. That's the depth of recursion. That's how many times I'm going to recursively call this branching function. And so if the depth ever gets to be larger than 2, I'm going to stop recursing. So this is the stopping condition on my recursion. And you always need a stopping condition or you'll end up with an infinite loop and, in fact, a stack overflow. That's where the name of the website comes from, is if you have infinite recursion, you'll end up overflowing your memory, which is stored, again, as a stack. So the idea is we say I'm starting at depth 0. Each time I call the branch function, I'm going to increase that depth by 1. So you can see that depth plus 1 here until I reach some maximum depth. And then I'm going to stop recursing. I'm going to return without doing anything else. What do we do with each branch? Well, we simply draw a line of the given length. And then we translate to the end of that line and do the same branching function again. So basically it's draw a line, move to the end of the line, draw a shorter line. Move to the end of that line, that's the translate, move to the end, draw a shorter line. So this just draws a series of shorter and shorter lines until we reach the maximum depth, which is 2. Currently, I'm using some fixed numbers like this 0.4. Later on, we'll change that and randomize it a little bit so we can get different snowflake shapes. But let's see what this does. This doesn't appear to do anything different. It's a little bit subtle, but in fact, each of these branches is a little bit longer because we're adding on to the end of it with this line. You can't really tell because I haven't changed the stroke weight. So that's the piece that I want to add now. Should have done this earlier. I want to make the stroke weight the length times 0.1. So that's the same thing that I did up here. I said the stroke weight is equal to the length that I'm doing, which here was width times 0.15 times 0.1. I also need to move this code and put it inside of my transformation. Otherwise, the stroke weight that I will end up with is whatever this function sets it to be. So I need to reset it for each branch. So as I draw each central branch, I have to set up the stroke weight, the rotate, before I draw the line. So here we go. And now you can see those recursive branches because they've gotten a little bit narrow. Not quite a snowflake yet, but we're getting there, okay? And think about how the recursion works. So this is a good time to look at the code, right, and understand it. I draw a line, that's this line here, and then I say, now draw a branch, that's my branch function. It makes the stroke weight a little lighter, and it draws a branch which is of length len for length, which was 0.4 of my previous branch. So you see this branch is 40% as long as this one. Then I translate to the end of that branch and recursively call the branch function again. So that's the recursion. I'm calling the same function again, but I'm using a length that's 40% as long, so a shorter length. And I'm increasing the depth by 1 so that eventually we hit a maximum depth. Okay, so we have the basis for a snowflake. Now what I need to do is draw the 2 branches that come off. So I said I want a central branch and 2 side branches. I'm going to do that by taking this code here and basically repeating it twice more, but with a rotate in each direction. And in order to make this work, I have to move the line inside of my matrix transformation. So here's the first branch. I'm rotating my whole coordinate system in a negative direction, 0.4 pi, I might have to play with that a little bit, but a little less than half a pi. And then drawing a line, translating to the end of that line, and asking it to repeat the whole process. And then the same thing. So here I've taken that same block of code, except now I'm rotating in the positive direction. So rotate in the negative direction, draw a line, translate to the end of that line, and redo the whole branching process. Get rid of that transformation and start a new one. And I'm gonna, not necessary, but move this code inside my block here. Go. Draw that new line, translate to the end, draw another branch. If you want, it's not necessary, but to make the code feel a little more consistent, I'm going to put a rotate 0 there. Rotating 0 doesn't do anything, but it gives the idea of I have a left rotation, a 0 rotation, and a right rotation. Okay, let's see what this does. And there we start to get a snowflake. And notice the power of the recursion here. We get to the end, and then instead of just drawing one shorter line, we draw 3 based on our transformations. One thing you'll notice that I messed up a little bit, which is fine, is only the left branch has the right stroke weight. And that's because we reset the stroke weight to make these little teeny branches at the end, and I didn't set it back to the heavy stroke weight again. So we can fix that simply by taking the stroke weight code here and doing what we should have done in the first place, which is putting it inside of each of these blocks. There we go, much better. Okay, so this gives us the same snowflake each time. And there's a couple of ways in which I want to vary it, and we're going to do that by making variables for our class. So we're going to give the class some data members. But the things that will affect how the snowflake looks are, 1, how much we scale down. Right now I'm always scaling by 0.4, but I could scale by more or less. 2, what these angles are. So I could make these angles larger or smaller. That would give us a very different shape. 3, if we wanted to, we could adjust how much the weight changes. I might not change that. I think I'll leave that. But you could do it if you wanted it as an exercise. So that's this 0.1 on the stroke weight. We can make that a variable. And then we can also vary what the color is each time. So there's a bunch of different changes that I will make in order to give us random snowflakes. So before making those changes to color, angle, and scale, I want to talk a little bit about the depth. So here we have our depth is larger than 2. That's the cutoff condition. If I were to make this say 1, let's look at what that does to the snowflake. Basically, it's going to say recurse less. So there you notice we don't have as much branching going on because we don't get as far in this recursive process of drawing more and more branches. And on the other hand, if I were to say make this depth 3, it's a little hard to see, but there are some teeny branches at the end that have been added because now we've gone 1 depth further in the recursion. This is what makes the snowflake a fractal shape. A fractal is simply any sort of geometric form that if you magnify it, you see a similar, it doesn't have to be identical, but a similar sort of pattern. And so here it turns out it is identical, right? This branching of 3 is exactly the same as that branching of 3 is the same as that branching of 3. So this is a classic fractal shape. And that's often what you end up with when you're drawing with recursion is you recurse and draw a smaller version of the same thing. So this is how we get fractal shapes. So the depth is another variable we may want to adjust as we go along. So let's begin by changing the angle. So the angle of our branches is determined by this minus 0.4 and this positive 0.4. And so what I want to do is make that something random that we can change. So I'll go to the beginning of the code and add a class data member, angle. And then the typical thing to do would be to create a constructor that constructs and sets that angle. But I'm not going to do that. Instead, I'm going to create a reset function that sets that angle. And the reason I'm going to do it as a reset function is so that I can call it repeatedly and have my snowflake reset and get different random snowflakes. If you've watched the video on fireworks, I did the same approach. We had a firework object that we could change using the reset function. So this is the percentage of pi that I'm using. So 0.5 is the upper range, that's half a pi. That will give me branches that are straight out to the sides to 0.25, which is like 45 degrees. So I'll get a random angle in that range. And then in my constructor, I'm simply going to call the reset function. And so I construct a snowflake, I call reset and pick an angle, but if I ever want to change the angle, instead of reconstructing the snowflake, I call my reset function. And so now that I have this angle, I need to actually use it in the code. So minus the angle times pi, plus the angle times pi. And I'm getting an interesting error message here. Notice that it says angle doesn't exist, and the reason for that is when I created my branch function, I didn't make it part of the class. So this function, branch, is not currently part of the class, and therefore it can't access this angle variable. To fix that, I'll remove that and put it here. And now my branch function is part of the class, part of the snowflake class, and it can access the angle variable. So you notice that error goes away. And if we run this, and we get a snowflake, looks about the same as before. If we run it again, a little hard to tell, but those angles are slightly different. And like I said, that's hard to tell if we just run the program individually. So let's put it into the draw loop, that it just generates random snowflakes the way we saw at the beginning. Display the snowflake, and then simply reset it. And this will not work real well yet because the draw loop is going so fast. But you can see those angles do keep randomly changing on each loop of the draw loop. So let's slow this down by using a slower frame rate. I'll do a frame rate of 2. So that's 2 frames per second. So every half second we'll see a new snowflake. There you go. And you can adjust the frame rate however you like, but you can see those angles are changing. If you want, you can change the bounds on how much they change by. So this is the basic idea. We take the key variables that define what the snowflake looks like the angles, and then we make it a data member of the class, and then we randomly set it every time we generate an object in the class, or we can reset it whenever we want. So now we can do that with the scaling factor, and we can do it with the color. Same idea as angle. This scale is going to be how much we scale the branch lengths. And again, you may want to adjust these bounds a little bit. I found that 0.4 to 0.7 works well. So we're taking our length and scaling it down by between 0.4 and 0.7. And now we have to use this scale in our code in quite a few different places. So here, when we first make our branch, instead of 0.4, we'll use our scale. Same thing here, when we recursively create a new branch, we'll use the scale. Here, when we create a new branch, we'll use that scale. And here, when we create a new branch, we'll use that scale. So before, where I had a fixed 0.4, now I have a variable scale. Another thing you could do if you wanted, although I won't put it in, leave it as sort of an exercise, is you could have a different scaling factor for this middle branch, right? This is the middle branch. Maybe that should be scaled down a little less, and so the main branch is longer and the side branches get shorter faster. I won't do that, but it's simple enough to do either by creating another variable or adding another factor in here. So notice that now we get all sorts of different sized snowflakes as well, depending on how much we scale things down. Right? And that gives you a nice amount of variety. And then the last thing, if we want, we can adjust the color a little bit. Same idea, new data member for the class. I was using 180. I found if you look up a color wheel between 180 degrees and 220 degrees gives me what I think of as nice bluish snowflake colors. And now when I set the color here, I'll just use that hue instead of 180 each time. So notice what I'm doing. I'm taking numbers that originally were fixed, and I'm making them into variables so that I can adjust them. And this is a very standard programming technique, especially for things like generative art. You start with a fixed variable and then you say, you know what, I want to make that randomly change a little bit to get more variety. So there we go, we're getting some subtle differences in color, although again, all sort of nice blues, and a lot of variety in our snowflakes based on the lengths of the branches and the changes in the angles. Other things we can adjust, like I said, you could put a different scaling factor for the middle branch. That'll give you slightly different forms. You could put in a random value for the depth of the recursion. So I'm doing a depth of recursion 3 here. We could change that to say 5, and what you'll see is we'll get much more complicated patterns because the recursion is going much deeper. I kind of like that, so maybe we'll stick with 5, or you could make this another data member in the class, and some snowflakes are simpler, less recursion. Other snowflakes are much more complicated because they have a deeper level of recursion. You don't want to go too far with that, or they'll just become sort of a muddy mess. Okay? So there we go, a good start on making patterns of fractal snowflakes. And from here, as I said, lots of different places that you can expand and explore with them. Thank you.